Hello everyone. Let's continue more on the dehydration of alcohols catalyzed by strong acid. There is one important aspect that you need to learn in the mechanism of dehydration. There are what we call a carbocation rearrangement. What it means is it could a hydride shift 1,2 from carbon 1 to 2, or an alkyl shift. There could be a methyl shift or hydride shift. This is CH3 minus, H minus could shift from position 1 to position 2. That's a carbocation rearrangement. Let me give you an explanation. It's very simple. It's just a finding to a more stable carbocation that could be formed. For example, if you have this alcohol, of course you have this functional group and you are treating it with H+, strong acid. What you're going to do would be the protonation of this OH, and that creates a water molecule that would leave easily. Then you'd form a carbocation. I'm just taking that you have already understood the carbocation formation in the dehydration of alcohol. This is the intermediate we have. But I'm trying to introduce now what is a carbocation rearrangement. It could be a hydride shift or it could be a methyl shift. So if it did this carbocation, if it didn't shift, if this didn't shift, the product that will be formed would be this, for example. By eliminating one of the hydrogen here, making a bond here, you could form this. So that's without rearrangement, without carbocation rearrangement. That's the product you see. But you could be asked, so why are we seeing this alkenes in the synthesis of the reaction? In the mixture you would find this product and that product. Where did they come from? So remember, there is a concept called carbocation rearrangement. Here, if you just look at this carbocation is a secondary carbocation. So this is a one position. On a two position, there is a potential either if there was a hydrogen or a metal, that would be shifting transfer to this, leaving the carbocation in this one. So after carbocation rearrangement, it looks like this. Why it shifts, I'll let you know why that is. CH3. Now the carbocation, this is carbocation, is now shifted into this. Hydrogen is still there. CH3 is there. Now this carbocation, if you look at it, this is a tertiary carbocation. You see why it moves the carbocation by this metal shift. This metal would shift to this carbon, 1 to 2, or just not to confuse with hydride. This is not hydride shift, this is metal shift. So it shifts here. Then when it shifts here, it leaves, because it goes with its pair of electrons, this neutralizes, and now you have a carbocation which is tertiary, which is more stable. Out of this is why you would get this product and that product. For example, if you just lose this hydrogen to make a bond here, you get this product, a very stable tetra-substituted alkene. Tetra-substituted alkene. So the reason why we have a carbocation rearrangement is in order to create a more stable carbocation. That is driven by the stability of this carbocation. So stable carbocation. So remember, this is a metal shift. What we have is a 1,2 metal shift. So by 1,2 metal shift, this is 1,2, it should be neighbors. The metal cannot jump from carbon 1 to carbon 4 or something like that. The shifts are always to the nearest carbon. So you should always consider not like distance carbons, but rather on the same 1,2 position. So carbocation rearrangement is simply to make sure that you have a more stable carbocation. This is what happens. So this is a rearrangement. This is a rearrangement happening. Rearrangement. So carbocation rearrangement is a way of creating a more stable carbocation. Hence, you get a more stable product. For example, this one is also created from this, even though it's minimal. By just losing, what happens is if you just lose from here one of the hydrogen, the CH2, this CH2 would be on this. So this is also coming from a rearranged one. But this top one is just from not rearranged product. So mostly the major product would be the rearranged one, because that comes from a very stable carbocation. And if we compare between these two, this would be the major one. So this is a major product. So in an exam or a test, if you are asked by dehydrating this, they may not give you this product, and they will say that this is a product. How did it happen? Then you should remember that a carbocation rearrangement from a secondary carbocation to a tertiary carbocation, and hence then the elimination happens to form this. So if you didn't know the concept of carbocation rearrangement, you would not answer this question. So you may not observe this at all in the reaction, but for you up to now, from what you learned, you would have just guessed this product, this one to give this. But the major one is actually this. So it came from a carbocation rearrangement. So the carbocation would be rearranged by a metal shift or a hydride shift. So we'll see now an example of a hydride shift as well, because either you should have a hydride, or either you should have a metal group here, or a hydrogen that can transfer easily, because the group that would transfer should be very small particles. That should be like metal, hydrogen. Large bulky groups cannot shift easily. So it's either you have a metal shift or a hydride shift to make a tertiary carbocation. So I'll give you more example on the carbocation rearrangement, for example, by having a hydride to shift to make a tertiary carbocation. Okay, let's elaborate more on carbocation rearrangement. So the whole purpose of the rearrangement that happens automatically or in naturally would be because you want to make a more stable carbocation. More stable cation is more, that's what's preferable. Let's see these examples here. So of course the protonation of that OH, the protonation of this OH or this OH is what gives, by losing water, that's what gives the carbocation formation. So I have three examples here. It's always not necessarily metal shift. If you have a hydrogen, you could make a hydride shift by leaving together with two electrons. So the formation of a carbocation for this looks like, after losing H₂O minus H₂O, that's step one, or we can say initial protonation, and then water leaves, carbocation forms right there where the OH was. But here you have a methyl group here. So if you just look at this, this is a secondary carbocation. Secondary carbocation. So what you ask yourself is the secondary carbocation could rearrange by carbocation rearrangement to a more stable tertiary? Yes. If I move one of either the methyl or the hydride from hydrogen, one hydrogen here, obviously there is one hydrogen, I can make this a tertiary because the plus comes here and then it would be tertiary. So remember here, between hydride and methyl, if you have a possibility, the first priority is hydride, which is the smallest one, to leave, not methyl. Because if you move a methyl, it will be just secondary, so you don't form anything. So hydride shift, 1, 2, hydride, H minus shift, would give us a more stable tertiary carbocation right there. So that's the whole idea of why you do a hydride shift, getting a tertiary carbocation. Stable carbocation is formed. After this, it's a matter of losing one of the beta hydrogens to make the double bond, right? So that would create more stable double bond, which is that. So that would be the dehydration product. So if you didn't make this shift, if you didn't thought of this shift, you could have a hydride or a hydrogen that was leaving from here, a beta hydrogen, the double bond would have been here. But the major product is this. So you could be asked, why is that the major product while we are dehydrating this? You propose a mechanism where there is a hydride shift, and that's the tertiary carbocation, that's the major one, not this one. From this one directly, for example, you could have gotten a product which looks like, without hydride shift, you could get this product. But this product is not seen when you analyze the product in your reaction mixture. You don't see this. You only see this because there is a 1,2 hydride shift. This is a predominant reaction mechanism. That's why you see that. Let's dehydrate this alcohol by protonating with sulfuric acid or any kind of toxic acid. Now I will have the carbocation to be formed like this. So I'm skipping the protonation step, just showing you the carbocation, and this is CH3. Now here, if you have a secondary carbocation, this is secondary. Now I want to make it a tertiary if there is a possibility. So if I shift this hydride as a whole to the next 1,2 shift, the carbocation would shift here, the hydride would shift there with its electron. So a 1,2 shift, 1,2 hydride shift again, not methyl shift in this case. A hydride shift, meaning that this hydride would shift there with its pair of electrons, so it leaves the carbocation on this carbon. So CH3, since both electrons have been moved together with hydride, you have a plus here, and this is satisfied now with hydride, no charge, that's already there, CH3. So now you'd see a product that looks like this is a more stable tertiary carbocation. The product, major one would be from this is this. and one H actually here. This would be the major product after carbocation rearrangement. Here I have this alcohol which could dehydrate by forming this carbocation. Now, if this carbocation, if you just look at it, this is secondary because it is attached to two carbons, and there is one hydrogen obviously on that. And then is there a possibility this can shift here and this become a tertiary? Yes. So if I do a 1-2 shift, hydride shift again, there is hydrogen here, don't always forget that. One hydride shift would give me this and that, two hydrogens now. Because there was one hydrogen here, one hydrogen is transferred a hydride shift to this carbon. That gives us that. Now, the major reaction product for this could be, for example, if I lose one of these hydrogens to make that bond, I would have a product which looks like that. So, as a summary, you could have a hydride shift or a methyl shift based on what you have and what kind of carbocation would make. That is the main, it could be in SN1 reaction where a carbocation could be formed, an E1 mechanism, it could be a carbocation. So always make sure that if you see abnormal products, meaning that from where you expect the double bond to be, maybe there is a carbocation rearrangement. So whenever there is a carbocation formation, make sure that that carbocation is derived from a very stable carbocation, meaning that not from the secondary. Here we made a tertiary actually, so this is a tertiary carbocation is formed. So always make sure to recognize whether there is a carbocation rearrangement or not in a reaction, so that you could justify what kind of product you get as a major product. So these are major products. Major. That's what you see in the reaction. Mixture, major, because of the carbocation rearrangement through a 1-2 hydride or a 1-2 methyl shift. It could be a shift of a hydride or it could be a shift of methyl. For example, here, if this hydrogen was a methyl group, not hydrogen, a methyl can also shift here, create a carbocation here to form the tertiary one. So it's based on what you have, whether you have a hydride or a methyl. It depends on the type of molecule you are just trying to solve the problem for. Okay, we'll continue more on this.